Revolutionary Perovskite Semiconductors, powering next-gen displays and electronics. Greetings to everyone. The topic of our video today pertains to a revolutionary advancement in semiconductor technology, where vapor-deposited tin-based perovskite transistors promise to transform next-generation electronics. Led by Professor Yongyoung No and Dr. Eugene Reo at Pohang University. This breakthrough leverages thermal evaporation to create high-performance P-type transistors with exceptional hole mobility and stability. These transistors rival commercial N-type semiconductors, offering rapid signal processing and low power consumption. Compatible with existing OLED manufacturing, this innovation could usher in ultra-thin flexible displays and integrated circuits. Without further delay, let us delve into our discussion. Picture this. Every time you swipe through apps or binge a series on your smartphone, tiny transistors, thousands of them, work like diligent gatekeepers, channeling electric currents to light up your screen. These unsung heroes, split into N-type, electron movers, and P-type, hole carriers, are the backbone of modern electronics. Yet while N-type transistors often steal the spotlight with their efficiency, P-type transistors have lagged behind. Why does this matter? High-speed, low-power computing demands both types to perform in harmony. Enter a game-changing discovery from Professor Yongyoung No and Dr. Eugene Reo at Pohang University of Science and Technology, joined by Professors Ao Liu and Huihui Zhu from the University of Electronic Science and Technology of China. Their findings, unveiled in Nature Electronics on April 28, 2025, herald a new era for P-type transistors. What's their secret? Tin-based perovskites, crystalline materials with a knack for conducting holes like a maestro leading an orchestra. Traditionally, crafting these perovskites relied on solution processing, a method akin to dipping a brush in paint and hoping for even strokes. Scalability faltered, uniformity wavered. But this team dared to dream bigger. They turned to thermal evaporation, a technique that's the gold standard in industries churning out OLED TVs and semiconductor chips. By vaporizing materials at scorching temperatures, they sculpted thin, pristine layers of cesium tin iodide, CSSNI3, onto substrates. And here's the twist, a pinch of lead chloride. This subtle addition transformed the perovskite films, boosting their crystallinity and uniformity, like polishing a gem to reveal its brilliance. The result? Transistors that dazzle with a hole mobility soaring past 30 square centimeters per volt second and an on-off current ratio of 10 to the power of 8. These figures rival commercial N-type oxide semiconductors, promising lightning-fast signal processing with minimal power drain. What's more, this innovation shatters two barriers of solution-based methods. First, it delivers unmatched device stability, lasting over 150 days in nitrogen storage, no encapsulation needed. Second, it enables large-scale arrays. Think 576 devices on a 49 square centimeter wafer. Compatible with OLED production lines, this technology could slash costs and streamline manufacturing. Imagine ultra-thin, flexible displays for smartphones, TVs, or even wearable gadgets, all crafted at temperatures below 300 degrees Celsius. Supported by the National Research Foundation of Korea, the National Semiconductor Laboratory, and Samsung Display, this breakthrough paves the way for vertically stacked circuits and high-resolution displays. Could this be the dawn of a new electronic frontier? The possibilities spark excitement for a future where low-power, high-performance devices are within reach. To support our channel's growth and ensure broader awareness, kindly hit the like, share, and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.